we will change our array so that it is now sorted. And then we can ask the question, can I get out of the loop earlier now that I know the array is sorted? So a sorted array can look like this. A sorted array does not mean that I cannot have duplicate items. I can still have duplicate items. So 5, 7, 10, let's say 11. If I want to look for the value 6, okay, I will probably keep my original search algorithm at least for now. So I would say 0 is not 6, 2 is not 6, 2 is not 6, 5 is not 6, 7 is not 6. Do I have to go any further?
No.
Why not?
Because 7 is greater than 6.
7 is greater than 6, so? But since it is a sorted array, it implies that everything after 7 are also greater than 6. Anything that's greater than 6 cannot be equal to 6. So I know at this point I don't need to look any further because there's no need. Okay? The way we optimized our algorithm is simply to add one more condition because we can exit now earlier. Or change the comparison, actually. We just changed the comparison a little bit. So we'll go back and look at this algorithm here. In a sorted array, we can speed up the loop as follows. This is still using the old way of doing things. Instead of saying that we stay in the loop when a bracket I is not k, if I assume the array is sorted in a non-decreasing fashion, that means I can change the condition here and say that we only stay in the loop when k is less than a bracket I. Am I right? No, it's the other way around. When k is greater than a bracket I. That's the only time we stay in the loop, when the array is sorted in a non-decreasing fashion. Is that making any sense? This is non-decreasing, which means they can have identical values. And I basically keep looking until k, which is the value I'm looking for, is less than the element I'm looking at. But I would say that this is still pretty slow. If you think about it, how do you look up a dictionary? Do you look up a dictionary from page 1 and keep going?
Look halfway in the middle, see if you're high or low.
Yep. So it's called a binary search algorithm. Yep. Go ahead.
I was going to say you look for the letter first.
Right. Most people
First
will look at
letter.
the letter, but the faster way is actually split. Look into the middle of the dictionary and decide which half of the dictionary may have the word you're looking for. Okay, which is not intuitive because people don't really operate like a computer, but that's the faster way to do it. Okay, so let's go ahead and talk about binary search, which is actually in this slide here. And the concept is quite easy. Let's say someone gives you a deck of cards. And the cards only have numbers, so it's easy to talk about comparison. It is already sorted, and I want to find out whether a particular number is in the deck. Okay, how would I do it? Assuming it is already sorted.
Divide it in half, and
The
the car is
quickest-
lower, and
Yep.
divide it again, and the car is lower, divide it again.
Exactly. So the quickest way to do it is what we call binary search, which is exactly what you just described. We take the deck of cards and split it, just about 50%. Okay, sometimes it's not possible, but we'll try to get as close as we can to an even split between the top and the bottom deck. We take the middle one out of between the two, the top and the bottom. We look at that card. If that card has the value I'm looking for, I'm done. I'm lucky. If it does not, I can always throw away one half of the deck. Because one half is less than the value that I'm looking for, okay, and the other half is greater than or equal to. Well, yeah, okay. Example. So let's say we have 0, 2, 5, 10, 11, 14, and 20. This is my array. I'm looking for a value, let's say 7, which is not here. So the question is, what is the pattern that I'm going to use to search in this array? Let's copy this onto the text here so we can capture it. Binary search is much faster. So here's my example. We have 0, 2, 5, 10, 11, 14, 20. Okay. We are looking for 7. Which one is approximately or exactly the middle of the whole thing?
10.
The 10 is, right? The 10 is. The 11 is not. Because we have exactly 7 elements. With 7 elements, we know exactly which one is in the dead center. It is the 10. How does 7 relate to 10? 7 is less than 10. Very good. So we'll go ahead and use the uppercase V to approximate, a less than symbol arranged in a vertical fashion. What is that telling you? Well, it's telling you that this element here cannot be the answer. But it's also telling you which half we can throw away. Which half can we throw away? The left-hand side or the right-hand side?
Right-hand side.
The right-hand side. Because if 7 is less than 10 and the array is sorted in a non-decreasing way, it also implies that 7 has to be less than everything to the right-hand side of the 10. Is that making any sense? In other words, in one single comparison, I ended up crossing out 4 elements in the array. With the 3 remaining, which one should I compare next? It will be the 2, okay? Because 1, 0, 2, 5, are 3 elements, and the 2 is right in the middle of the pack. 7 is greater than 2. Well, if 7 is greater than 2, it implies that 7 is greater than 2 and also everything to its left. So that means I can now eliminate these 2 elements. I only have 1 left. Now we have the 5, and we can say that 7 is also greater than 5, which means I can eliminate everything, including 5, and everything to its left. Do we have anything left?
No.
Nope. And we're done. The algorithm only takes 3 searches or 3 comparisons to conclude that 7 is not in the array. Yep.
What if there's multiple, like say you're looking for number 2 and you have multiple 2s, it won't return the first version of the 2. What if you want to know all the instances of the 2? Can you still use a binary search?
Binary search can only confirm whether it is there or not. It does not count how many instances there are. So if you're only interested in is it there, yes, binary search will still work when you have duplicate values. If your question is how many there are, then you need to modify the binary search so that by the time you locate one, you have to look left and right to see if there are multiples of the same thing. Yep.
The other day you were using the boxes example and containers in the boxes. Is it, you sort of today said that you could have multiple containers inside the boxes with the same value?
Yeah.
Yeah. Could you have multiple boxes inside other boxes with the same value, or that wouldn't work?
Well, but you cannot say a box has a value because a box contains individual
Well, with the same,
items.
like the same letter, the same name, it wouldn't work?
It would not work because
Yeah.
anything inside a box has to be numbered and not named.
Okay.
Yep. So once you introduce a box, then the items inside the box, whether they are boxes themselves or container themselves, they only can be numbered but not named.
Okay.
Okay. So there's that restriction.
So what if the other boxes, the sub boxes had? What if the boxes, 2 of them had the same number?
They cannot have the same number. Yep. Because they have to be consecutively numbered, starting from 0. Okay. Very good. Now this one doesn't seem to be that much of a gain because if I'm smarter, using the linear search algorithm, I would say 7 is not 0, 7 is not 2, 7 is not 5, 7 is not 10, but at this time I can stop right away In other words, using the linear search algorithm, it seems like I would just have to compare just one time more than binary search. So is it really worth the time and the trouble to do binary search? That's the question. So to understand or to understand the power of binary search, let's say we have a universal phone book for the entire population of Earth, okay, the human population of Earth, which is approximately, what, 6 billion or so these days? Is it 8? Already? Wow. Okay, well, 8 billion is fine. Okay, so the question is, if I have a universal phone book and each person on Earth has an entry, it's sorted by something, could be your ID number or whatever, how many times do I have to compare in this super big, huge phone book with 8 billion entries before I can confirm that a person does not exist?
You have to divide it in half, and then divide that in half.
We keep dividing it by half, but how many times do I need to search before I can confirm that a name does not exist in the phone book? With 8 billion, it is 33 times. It is 33 times. Okay, there's a quick and easy way to figure this out. In other words, I'm asking, with this or approximately this many entries in a phone book, what is the closest power of 2 to this thing? 2 to the power of what is about the same order of magnitude? That's the question. Now, you can use a calculator. If you have a calculator, you take the natural log of this number, you divide it by the natural log of 2, and you get the answer right away. Okay? But if you don't have a calculator, there are quick ways to do it too. We know that 8 is 2 to the power of 3. That's the easy one. What about the thousands? Well, as it turns out, 1,000 is approximately 2 to the power of 10. So this is 2 to the power of 10, this is 2 to the power of 10, this is also 2 to the power of 10. So the entire number is approximately, okay, well, this is exactly that, but this number does not equal to this number. So this number is approximately this number, which is exactly the same as 2 to the power of 33. Okay? So that's why I can just look at a number and I can guess the closest power of 2 to that particular number. In this case, 33. In other words, you give me a phone book with 8 billion entries, I only need 33 comparisons to confirm that a name does not exist in the phone book.
But to sort that, we make a sorted array to sort an array. Doesn't it have to do a linear search first to sort it?
Sorting algorithms is interesting too, because sorting algorithms also depend on, is the array already sorted when you introduce a new item? Okay, because if you can guarantee that the array is always sorted by the time you insert a new item, that's a different time. That's a different complexity. But we won't get into the sorting part. We'll just talk about the searching part now. What if the population of Earth doubles again to 16 billion? How many times do I have to compare? 34. Exactly. I add one more comparison to cover twice the size of the phone book. Okay? That is the power of binary search, because every time you compare, you can throw away 1/2 of the entries. Okay? So are we starting to kind of appreciate the power of binary search? Okay? The next question is, how do we implement binary search? Okay, what is the nature of binary search anyway? Is it repetitive?
Yes.
It is repetitive. Okay, so we say loop and loop. Do we want this to be an infinite loop?
No.
No. So when do we get out? Interestingly,